Good afternoon, everyone. My name is Gang Xiao, and I'm the new chair of physics department. So today we're very happy to have Professor Michael Koslitz here. Still is on sabbatical leave. Just came back from Finland, right?
Yep, Finland.
And he's here only for 4 days. Tomorrow he will be going to Boston and then to South Korea for probably another 18 hours of flight. So he has been very exhausted this week, but one thing he really likes to do is meet all of you and answer questions. So as you know, right, the Royal Swedish Academy of Sciences awarded this year's Nobel Prize in Physics to one of our own, Professor Michael Koslitz, along with two others for the discovery of the topological phase transitions and topological phase of matter. And I have the original paper, which is here, and its title is Ordering Metastability and Phase Transitions in Two-Dimensional Systems by Koslitz and Thouless. It's published in Journal of Physics C, Solid State Physics. It is not a high-impact journal, but you only need one paper in anywhere to get a Nobel Prize. That's the message, yeah. And this paper alone, published in 1973, to today received citations of 6,879. That's like 1 billion hits of YouTube video in physics, yeah. It's not easy. If you get 100 citations, it's already a good paper, but this is nearly 7,000. And he also has another follow-up paper in 74, which he received 2,384 citations. So this work has received about 9,200 citations. And for those of you who are interested, this is a very well-written paper, and I think all of you can understand this. Okay, so get a copy and try to read it. If you're a physics major, you have to make sure you understand. This is a homework, okay? Yeah. And the other paper I want you to read is the BCS paper on superconductivity, and that is one of the most beautiful paper in theoretical physics, in any theoretical physics, okay? It's just beautiful, and I think by the end of you study physics, even mathematics, you should be able to understand that paper as well. So ordinary matter, right, refers to things such as gases, liquids, and solids. And exotic matter is, very exotic, and they behave as such. So at extremely high or low temperature, it begins to exhibit very strange properties. At a low temperature, metals can turn into superconductors, or liquid can turn into a superfluid where there's no friction or viscosity, both in resistivity and in resistance to electrical current and also flow. So these will allow them to flow with no loss of kinetic energy or frictionless. It's a wonderful, wonderful state of matter. And a superfluid is also formed by vortices. And if we stir these vortices, they will rotate indefinitely, okay? As long as the temperature is low. The other example is a superconductor at low temperature. They undergo some sort of phase transition, which can be characterized as XY model, the Koslitz-Thouless transition predicted by Professor Koslitz. In the 1970s, along with David Thouless, Professor Koslitz developed the theory of topological phase transition, and the theory explains how matter can transition between non-exotic to exotic states. Two publications in Journal of Physics, as I mentioned, received lots of citations, and they established a field where the topological defects in matter is very important, okay? And ever since then, today, we have an explosive interest in this type of materials, starting with quantum Hall effect into the electron gas, subjecting to a very strong magnetic field. But today, you can actually, without the magnetic field, you also can have the quantum Hall effect, okay, which is a topological state of matter, of electron state. And also, there's a new class of material called topological insulator, which is very, very strange. The material itself is insulating, but electron can conduct electricity on the very surface. Okay? This is a very interesting quantum mechanical effect, and you can take advantage of this to make some of the most sensitive magnetic sensors, or can potentially use this for quantum computing, because the phase of the electrons in this cathode material, it plays the important role in electron transport. It's not just the amplitude of wave function, it's the phase of the wave function. So the findings of Professor Karslitz, Thouless, and Haldane have had a major impact on electronics, although Professor Karslitz do not want to admit that. They will surely do so well in the future. As the acting chairman of the Nobel Committee, Niall Martinson, put it when announcing their award, today's advanced technologies, take for example our computers, relies on our ability to understand and control the properties of the materials involved. This has paved the way for designing new materials with novel properties, and there's great hope that this will be important for many future technologies. I can tell you, right, within the next 10 to 20 years, silicon, which we call CMOS technology, will reach its limit, okay? Now we can continue to improve future electronics, but in order to make quantum computer or computer supporting artificial intelligence, you need new kind of devices, new kind of physics, okay, new kind of electronics, and we are looking for this. And physicists, we try to find the next generation of materials or devices which can replace silicon. Okay. Professor Karslitz joined our department in 1982. He has been an inspiring and wonderful teacher and mentor to students, and also an inspiring and invaluable colleague to us faculty members. Professor Karslitz grew up in Britain. His parents fled Nazi Germany in the 1930s. He received his secondary education at Robert Gordon College and Edinburgh Academy, and he finished his bachelor degree at Cambridge University in 1965. And just 1 year later, received his master degree, and then just 3 years later, he got his PhD degree from Oxford University. He did his postdoc work at Torino University in Italy, and had done research work at Cornell, Princeton, Bell Lab, and Harvard. He was on the faculty of University of Birmingham in UK in the latter half of the 1970s before joining us in early 1980s. So we were very happy as a department to have had him here since then. So here at Brown, he has continued his groundbreaking work in developing numerical methods for studying phase transitions, the growth of surfaces in thin films, and also the superconducting arrays. In the last few years, he has worked on disordered systems such as spin and gauge glasses, and also on the growth of eutectics. Yeah. Long before the Nobel Award, the scientific community has widely recognized his work. He received the Maxwell Medal from UK Institute of Physics in 1980. He has been a fellow of the American Physical Society. In year 2000, he was awarded the Las Onsager Prize, the highest in statistical mechanics, by the American Physical Society. That's the society for all physicists worldwide. For the introduction with David Thouless of the theory of topological phase transitions, as well as his subsequent quantitative predictions by means of early and ingenious application of the renormalization group. It's a kind of mathematical tool. So students, how inspirational it is to have one of your own professor as a Nobel winner. The sky is the limit in our exploration of nature, and you are in the middle of it all. And we have relatively a small physics department compared with our peers. We have 27 faculty members, but we already have 2 Nobel Prize winners. And if we count Professor Gerald Gronick, who was the co-discoverer of Higgs boson, right? We probably have 2.9 Nobel Prize winners. Yeah. And I think that this is not ending right now, and we are looking forward to our future Nobel laureates, probably among all of you here. Okay. And I just want to let you know this is a democratic field, and if you work hard enough, love physics, you have equal chance of getting your Nobel Prize. Yeah. So with that, I like to. So the way I'm going to do this is have all of you, if you have any questions about research, about his personal life, or about anything else, political views and stuff. Please feel free to asking. We have about an hour of time. And please come here to use the microphone and just introduce yourself and ask anything you want. Okay. Who want to ask the first question? Let me just break the ice a little bit. Okay, let me just ask you a question. And then, because a colleague of mine, Professor Palkovich said, how soon after doing your work did you realize that it might garner you a Nobel Prize?
I never thought it would actually get this far. David and I knew we'd done something good when we sort of did the initial work, because we managed to solve a problem that had been bothering physicists for quite some time. So, as I say, we knew we'd done something good, but remember, it was purely theoretical at the time. David was still is, a pure theoretical physicist, and I am too. I hate experimental work because it seemed that whenever I went into the laboratory, things just stopped working. So I decided that perhaps it's best for everybody if I don't go near a laboratory. And so that's why I became a theorist. I guess, I don't know what else to say on this topic, but.
Okay.
Hi, Professor. I'm a junior. I am very interested in statistical mechanics, and Brown actually, not many people know this, but Brown has a long history of advances or having professors here who have advanced statistical mechanics very widely. So it seems like every 20 years or so, there's a very great leap forward coming from Brown or a Brown professor. Where do you think the next leap forward will come, and what do you think it'll look like?
Your guess is as good as mine. How one can't tell. And after all, physics is full of unsolved problems, and so anybody can have a bright idea and work it out and become famous. That's really what physics is all about.
Thank you.
Presumably, you didn't finish this work in a day. So, were there periods where there was thoughts of giving up the problem, or despair, or elation, or any sort of emotional ups and downs when you were working through this? In fact, how long did it take you to from start to finish on this project?
Okay. Well, the initial work was fairly quick, because it wasn't that sophisticated, in the sense that the idea was based on electrostatics, dielectric theory, and that's how the original problem was posed. David and I almost completed the work, but we messed up in some apparently innocuous way. If we hadn't made a stupid, unnecessary approximation, we would have derived everything in the first paper. But as I say, we made an unnecessary approximation, and so it left a lot of work to be done. But so the first paper took, I don't know, 2-3 months. It wasn't that long. Later on, subsequent work took rather longer. For example, my development of the more sophisticated version of the where I had to basically construct a renormalization group to do it. That took a lot longer because in some of our initial discussions, David gave me some literature to read. And one of these piece of literature was a preprint. Remember, I'm talking about the days, pre-internet days, which most of you don't realize actually there were days where there was no internet. And so communication wasn't that fast, and so the way new physics was communicated was by preprint, which was typed, or no, and I'm talking about days even before Xerox machines. So that copying was done by typing something on some sort of skin, which perforated the skin, and then you put this through some machine, cover it with ink, where the ink went through the holes, and that's how you produced preprints. And so then you would send out the preprints by snail mail to your colleagues, maybe 100 or so, and this is how physics was, new developments were communicated. So David passed me this preprint written by Anderson Yuval, and I spent about 6 months trying to understand what on earth they were doing. And then when I finally understood what they were doing, then I thought, okay, this looks interesting, it's worth trying to figure out exactly how it's done, how they did it. And so I spent altogether 6 months doing nothing but reading and rereading that paper and trying to reproduce what they'd done. And when I'd done that, sort of the light flashed, and I realized they could apply their ideas to the two-dimensional films of helium and two-dimensional XY model. And so that was how the second paper was really written. But that took a while. It was must have been a year working on that, at least a year working on that one.
Oh, so it really took persistence, is that right? You knew this was a great
no.
problem to work on, or you didn't have anything else to work on? Or?
No. Certainly partly didn't have anything else to work on. Well, you see, the problem started when I was a high-energy physicist and had been doing long, tedious calculations, and I didn't seem to get any return for them. And then also, about 2 or 3 times, I just finished a calculation. Was about to write it up and send it off for publication when the preprint arrived on my desk, doing exactly what I'd just done. And this happened about 2 or 3 times. And one of these papers all came from some group at Berkeley, and one of the principal people in this group was our esteemed ex-chairman, Chung-Yi Tan. So I have to thank him for making me change from high energy physics to condensed matter, because at this point I gave up and went around the department asking if anyone's got some problem I could look at. I found myself in David Thaler's office listening to his weird and wonderful ideas on, remember, I hadn't done any condensed matter physics. I didn't know anything about it. Didn't know anything about statistical mechanics. And he was explaining about weird and wonderful things like dislocations, like vortices, and so on. And then he was explaining how these things interact with each other, and so on. And it all made sense to me. So I got very motivated and tried to work out what was going on. So I was very motivated. I need to understand how all this stuff fitted together. And so that's what kept me going.
Okay, here's another weird question. I got some questionnaire from somebody at like the National Institutes of Health or doing some survey of who should get their name on the paper first, right? And there are all these questions. Of course, in my field, the senior investigator puts his name on last, so none of this applied. But how about in your paper, Kosterlitz Thuos? Is that alphabetical order? Is that right?
Yeah, strictly alphabetical.
Okay. You got that right, huh? K, T. Okay. I got it.
Exactly. No, I mean, that was the convention in Britain at the time, just alphabetical.
Okay. Good enough.
Hi, I'm Kara. I'm a junior in physics here. So you answered this question a little bit for the specific research project that you worked on with Professor Thallis, but you mentioned how many unanswered questions there are in physics, and I think every physicist struggles with trying to pick which question they should pursue that might be the most productive. So I was wondering how you personally pick the most interesting research questions in all the stuff that you've been doing recently.
Okay. Initially, I picked them because Thallis told me they were interesting problems. Of course, I remember I didn't know what I was doing at the time. Later on, it was more a matter of picking a problem that I thought I could do. And so later, when I no longer cared about getting grants and things, I just tried to do things which interested me. So, in really picking the problems, I don't know how to describe it. It's, it's a matter of being. The essential thing is to be in the right place at the right time. In other words, you have to have the right supervisor or colleague who can throw out some idea, and you pick it up. So that's being in the right place at the right time. Beyond that, I guess really you need to know some mathematics. That's important. And you need to be fairly skilled at it, at least doing the manipulation. It doesn't matter so much if you don't understand it so well, as long as you can do things with it. And that is the important thing. After all, in physics, mathematics is a tool. Physicists in general don't care about a particular piece of mathematics. You just want to use it. You know, like digging a ditch, you want the best spade you can get, the one that makes life easiest. So that's what mathematics is. It's the tool. And so, the problem is really find something that interests you, and then hope you can do something with it.
Great. Thank you.
I'm sure you have more questions, right? Please feel free. So Professor Derek Stein asks you, what recent paper or talk has impressed you most?
Oh boy. I think the papers that have impressed me a lot recently have been the ones on the statistical mechanics of small systems, Maxwell demons, and things like that, because it can actually do experiments now on some fundamental things in statistical mechanics. So those are pretty interesting. And then there is some stuff on dissipation in quantum systems, because after all, when you learn quantum mechanics, there isn't any dissipation in the quantum mechanical setup. So, but of course, life is quantum mechanical, and we know that there's lots of dissipation, and so it's interesting to see how this can all be incorporated.
Hi, Professor Kosterlitz. It's always fascinating to learn about the interconnectedness within physics, in particular between high energy theory and condensed matter theory. There's often a fertile intersection. And I was just curious to know if you're aware of any applications of the Kosterlitz-Thallis phase transition to particle physics or cosmology. Obviously, there are phase transitions that are very significant in early universe cosmology, for example.
Personally, I'm not aware of anything, but I'm sure some cosmology will find some connection. But I don't know of any connection.
Hi, Professor. I'm a freshman planning to concentrate in astrophysics. In your opinion, where do you see the future of physics going in terms of research?
I guess that's the $640,000 question, because if I could answer that one, I could make myself quite a lot of money and be wealthy, and work on the appropriate problems. But to me, physics, is a never-ending thing, because there's always new problems. Even if one thinks that physics is dead, as was mentioned some years ago, but even so, there's always new problems. And just think for a moment. You look out your window in the morning sometime. There's lots of unsolved. You can see lots of problems out there, just looking out your window.
Right.
So I don't believe that physics will ever really come to a halt.
Right, but if you were to say if there's like a certain field that interests you the most, that you think will like have a lot more research in the upcoming years, or is there just a field in general that you're like super excited about?
One of the big fields, of course, is out of equilibrium statistical mechanics. In the real world, basically nothing is in thermal or mechanical equilibrium. Just look at your lamp or your window glass, right? I mean, that's not an equilibrium state, because the equilibrium state of the window glass is a puddle on the floor. And so it's out of equilibrium processes that I think are the wave of the future. How systems evolve with time. I mean, if one makes a reasonable assumption, which to me sounds very reasonable, that every system you look at is trying to get to a state of equilibrium. It's like you and me. We're lazy, we take the easiest route. And so most physical systems, all physical systems, passive systems, are the same. They're going to take whatever way is the easiest to come to its thermal equilibrium or stationary state. And so that problem is more or less solved. I mean, how a system approaches equilibrium. At least one can write down some equations which lead to the unknown answer. But if you have a system which is driven, you drive your system out of equilibrium, but you keep the driving absolutely constant, then many systems of that nature come to what is called a stationary state, where the state is time independent. And so to me, an interesting problem is, if you wait long enough with such a system, does the system come to a unique stationary state? No matter how you start the system off, will it always come to the same stationary state or not? And that's a rather more difficult problem. And problems of that nature are just sitting around waiting to be solved.
Hello, Professor Kosterlitz. I'm a first-year grad student. I'm interested in high energy theory. So I'm curious when you mentioned that you were doing the calculations, because I guess that's a major chunk of work for the next few years that I see in my future. But then at some point you got disenchanted. I'm paraphrasing, of course. And you switched to more interesting problems. So my question would be that, as somebody who's sort of once been there but then removed, and this was in the 70s, if I'm getting the timeline right, and that's a lot of interesting things have happened. I mean, it was probably a very exciting field back then. It still is, but there are certain questions that are raised, like, can we find the next, can we find supersymmetry, etc. So my question is, how would you say it has evolved over time as like once insider but now an outsider?
Well, to me, I mean, okay, the reason why I gave up high energy physics was because this was before the days of gauge theories. Nobody knew anything about gauge theories except, the standard gauge invariance and electrodynamics and stuff like that. But these gauge field theories didn't exist. You know, there's pre-'t Hooft and so on. And so, but now high energy physical field theories have taken on a new life because a lot of, you know, there's a lot, it all makes much more sense now. And, you know, all the calculations one does seem to actually give you something. Because it's so, as I say, in my day, it was pre-gauge theories. And so all these the fourth field theories and all that sort of stuff. And doing calculations and things like that are long, tedious things, and we weren't really getting anywhere.
Okay. Thank you. Yeah.
Next, yeah.
Hello, my name is Ilju, and I'm working at the postdoc as a postdoc in engineering department, but I do have a PhD in physics. So I'm working on the fluid dynamics, which is very kind of interdisciplinary in terms of physics. So I recently read, I mean, if I go to PRE or the statistical mechanics journals and then read the paper, then there are obviously some papers which is trying to solve the very physical problem, like the non-equilibrium statistical mechanics or something like that. But there are lots of portion of them are applications to the physical principle into another physical system, or even the metaphysical systems, such as, I mean, the network theory is applied to like non-physical systems such as economics or those kind of systems. So my question is, do you think the field of physics is determined, I mean, you can say some domain of research could be taught by physics by the methodology or by the topics?
That's a good question. I don't have an answer to as usual, but one thing that physics training does give you is an ability to solve problems, which is definitely lacking in many other disciplines. And that's why physicists are so much in demand, you know, in finance, for example, because physicists are trained to use whatever branch of mathematics it seems to work. And they don't really care too much about the origins of the mathematics, as long as it makes sense. And so physicists tend to think in a different way, I think, in a different way to most other fields, where they are problems oriented towards solving a problem or solving a class of problems without worrying too much about the tools to do this. I mean, just use whatever tools are available and whichever tools work. So whatever branch of mathematics does the job, they will use. And so training in physics is very, very good for problem solving. And after all, the world is made up of problems.
So if I add one question, then if you say the problem solving, then what do you mean by solving a problem? Like,
well, for example, many physicists who can't get jobs in say in physics end up working in finance because they're very good at solving the sorts of problems that crop up in finance.
So predictability is the important.
You know, they will cheerfully use probability theory to predict the most likely outcome of some investment. Mm-hmm. And somehow physicists seem to be good at this sort of thing. Physicists also can actually are trained to model situations and then go ahead and solve them. Because physicists have, you know, all of physics is full of things which not many people have thought about, so they don't quite know how things work. So physicists who thinks about these problems, they have to construct a model of how their system works and go ahead and try to solve it. So this is, I think it's one of the wonderful things about a physics training, is this problem-solving ability one has. And after all, much as I respect applied mathematicians and so on, the ones I've talked to seem more interested in the tool than solving the problem, you see. For instance, I remember talking to some applied mathematicians at a PhD thesis defense. And this was on stuff that I was fairly interested in. But then the PhD candidate was an applied mathematician. And to my surprise, he seemed to be more interested in the computational aspects. And whether, and you know, the sort of question they were asking is whether the problem is computable in the first place, which to me, as a physicist, is crazy. I mean, after all, you find out whether it's computable by just putting on the machine and seeing if it works. Never mind the theory, which may take, you know, forever to work out, but it's much quicker to just suck it and see. It's a completely different attitude, and I believe that the physicist's attitude is more productive, where you just go ahead, you could model your problem, and then try and solve it. One never ask questions is it soluble? You know, solvability and stuff like that. You just go ahead and see if it can be done. And if you can solve it, then by definition it's solvable.
Thank you, Professor.
Okay. Yeah. Next question.
Hi, Professor. I'm first year graduate student. My question is, what do you think about unified field theory? And something, is there exist a theory to explain all of the four fundamental interaction?
You're asking the wrong person.
I heard you have done some research about the high energy theory.
Oh, but that was many, many years ago. I said this was before even the days of gauge theories.
So
I mean, you know, the only gauge theory that existed then was electrodynamics. And so, and that wasn't really recognized as a gauge theory itself, but it was more, you know, it was the only soluble field theory in existence then. Of course, these days, you know, many, many gauge theories and so on, and so there's a lot of, you know, but where this is going, I have no idea. I mean, the mathematics involved there is way beyond me.
Thank you very much.
Welcome.
Professor Kostelis, congratulations. I'm a professor in engineering, and I'm going to ask a rather light question. So what attracted you to Brown, and what has kept you at Brown for the last 30 plus years?
What attracted me to Brown, okay, it's a slightly complicated story. I was at Birmingham University, and at one point they offered me a research professorship, which I thought, okay, that sounds nice, I'll take it. I was also in the process of applying for, you know, all want to go to the States, so I was in the process of applying to various places in the States. And I got a couple of offers, but I got an offer of a tenured full professorship from Brown. And all the other offers in California and so on were for untenured positions. Since I in Birmingham, I had a tenured position and kids, a family, kids and so on. I thought that, well, okay, the risk of losing my job, being terminated instead of getting tenure, was not high, but it was there. And so I decided that the offer of a tenured full professorship sounded very attractive because Brown is a good place. Not the greatest, but it's good. Where does it rank? I can't remember. In your research, I don't know, sort of number 15 or something like that. I did get offers from higher ranked places, but again, they were untenured positions, so I decided no, I prefer the security is also very important. And since then, I've been happy at Brown.
So I'm sure you had other opportunities, but you decided to stay.
Well, I haven't had other offers.
Okay.
Haven't been pouring in yet. Who knows? Who knows what's going to happen? But at my advanced years, I don't think it's worth moving.
Oh, yes.
Thank you.
Okay.
So I have another question that is also a little bit lighter. So you've spent a lot of your career traveling and working outside of the US and even outside of Britain where you grew up. So I'm curious about what you see as some of the challenges, but also the distinct advantages of like a more internationally integrated and cooperative scientific community.
Good question.
Well, I mean, of course it's an advantage of travel internationally. You can meet different people, different ideas, and you get to know people from other parts of the world, so you quickly learn that they're exactly the same as you are. So you sort of lose any fear of foreignness, if you wish. So that's one of the nice things about this field, that one can travel a lot and meet all sorts of other people, other ideas. And it's quite amusing because maybe I'm right, maybe I'm wrong, but it seems to me that in certain countries, people's minds work slightly differently to Western minds. And I find this extraordinary, that because the thinking processes just seem to be different, slightly different. And we've had some very strange interactions because of this.
Thanks.
You're welcome.
Hi. Thank you. Okay. So I'm a sophomore, and I am studying both like chemistry and physics. And next semester, I've actually noticed that you're teaching a statistical mechanics in physics department, and also there's a chemistry department, statistical mechanics. And then so I am first of all, I don't actually really know what statistical mechanics is, I think, and also I mean I kind of learned it in biophysics, but I don't know. And so I was wondering, like, what is exactly like a difference between a chemistry-oriented statistical mechanics and a physics-oriented statistical mechanics?
You should definitely take physics, okay?
They're basically the same. It's just that I think chemistry and physics, the focus is slightly different. And so the courses will seem somewhat different, but the teacher basically teaching the same material. It's just the emphasis is slightly different between the two, chemistry and physics. For example, one of the best statistical mechanicians ever is Michael Fisher at Maryland, and he was in the chemistry department at Cornell. Although I guess you'd say he's more of a physicist than a chemist. But he was definitely one of the best statistical mechanicians around.
So like the physics, like more like I guess the pure statistical mechanics is very much applicable in like in understanding a lot of the chemical processes, would you say?
Well, I'm biased. And so to me, statistical mechanics as almost the king of subjects, because in principle it should be applicable to any process in physics involving many particles, and in the same way it should be applicable to almost any chemical process.
Okay, thank you.
So with the Nobel Prize, the new Nobel Prize, the ranking of the physics department here will be much higher, yeah. and the difference between our university and other universities here, Nobel winners teach both undergraduate and graduate courses. So you have a lot of opportunity to work with Professor Kosterlitz, use him as a mentor or supervisor for your PhD thesis, and for your senior thesis as a concentrator. Yeah, so you have this opportunity available to you. Next question, yes, please.
Hey, sorry, I'm like kind of boxing here. So what do you think? How important do you think it is to like teach, like get a broad audience for like your research, and how important do you think it is to just like talk to academia? Just wondering.
Sure.
Well,
my research has always been focused towards, strictly physics people and relatively advanced people doing physics. I'm not the greatest undergraduate teacher, unfortunately. I wish I was better. I mean, for my fellow Nobel laureate, Leon Cooper, he apparently is a fantastic teacher. But I don't have the same, if you like, rapport with students, unfortunately. So my teaching skills aren't as good as Leon Cooper's. Right, so I really don't know what else to say.
Just remember to get your Nobel Prize, right? The best chance is to work for a Nobel Prize winner. Next question. So now you get the you already got the Nobel Prize. What's your next prize or project you're working on?
Well, now I feel that I'm in a position to do exactly what I want to do. I don't have to worry too much about doing things in order to get the next grant. And so I feel I'm in the position to do things that interest me, whether they're fundable things or not. And so I'm not sure what I want to work on. I mean, I have been working on a problem which I think is important, but it's not working as well as I hoped. So I may have to change a bit.
So, did your parents give you any special food when you grew up?
Oh, good Lord, no, because my father was a German Jew, and German Jews weren't too popular before the Second World War, I beg your pardon. And so in 1934 or something, my father realized that life in Germany was not good. And so he managed to arrange, a job in Britain and moved. And then my mother, who came from an Aryan family, almost, they had sympathies with the Nazis and so on. And so my mother came over to Britain as well, and they got married in Glasgow because they couldn't get married in Germany at the time.
Okay.
And so that's the story of my background. It's a bit unusual, but nevertheless, that's who I am.
And this year, all the American Nobel Prize winners are immigrants. So how do you how was it like growing up in an immigrant family in Britain?
This is okay, you have to remember this is wartime Britain. And so my parents decided that it was not a good idea for a small child to run around in wartime Britain prattling in German. So they taught me only English, didn't teach me any German. My father was an academic. He worked at Aberdeen University, where he stayed for the rest of his life. And my mother, she actually didn't work, although she, in Germany she was a lab assistant. And basically my parents, because as a young kid I had fun. And then when I went to, later on I went to school, my parents let me do exactly what I wanted, study exactly what I wanted to do, what I wanted to study. And so they didn't really influence me. I don't think they influenced me very much. Although my father used to take me from time to time, as a small child, to his laboratory, and where he was a physiologist. And I found it quite interesting, except one visit, I found in his wastepaper basket a cat with his head cut off, with his skull cut off, which wasn't very pleasant. I mean, things are a bit different in Britain, and so on. So he'd been doing experiments on cats by sticking needles in the brain and giving electrical impulses. And somebody had been a bit sloppy and just thrown the dead cat into the wastepaper basket. And I was, as a 10-year-old, 12-year-old, I was a little bit put off by that. So I decided that anything associated with medicine was a messy sort of subject, and involving experiments on cats and so on. And so I decided, no, I don't fancy doing things like that. And so I had some talent, mathematical talent, and I could understand the physics and so on. And so I just basically followed my heart. And so my father had always wanted to do theoretical physics, but his father wouldn't pay for him to study things like nonsense like that. So he became a medic. And so my own parents were quite pleased when I had this bent for maths and physics. And so quite pleased when I chose that track.
So your father was a well-known scientist. So was your childhood dream to surpass your father?
No, no. I decided when I was, child of some age, I don't remember, I was thinking, now, it's not a good idea to go into medicine, because if I were to go into something medically related, and you just hear the conversation between some of my colleagues, some of the colleagues say, who would say, conversation was something as follows: yeah, young Kosterlitz, he's quite good, but he's not a passionate old man. So, and so I thought, best thing to do is stay away from that field. And so that's basically how I went into physics.
A question here.
Good evening, Mr. Kosterlitz. I'm a freshman and I'm concentrating in physics. And I was wondering if at any point in time maybe you're doing your undergrad studies, if you thought of maybe switching over to mathematics instead of physics.
Oh yeah, certainly I did. I was at Cambridge, University of Cambridge in Britain. And at one point I thought, maybe I should, mathematics sounds pretty interesting, maybe I should change over to that. So I went and tried to change, but they wouldn't let me. So I continued in physics.
So now mathematics
which I think was a good thing.
So mathematics is just a tool now for us to use.
Well, for physics, physics is just a tool. Right. It is the language of physics, so that's what If you're going to do physics, you have to speak mathematics.
Thank you.
Were British schools you went to tough? Did you have a better education there?
The education in Britain is different. It was different in my day. It's changing out now. In my day, the schools I went to, okay, basically your education till you're about, like, I don't know, 15, 16, was conventional. Several subjects. Yeah, we did, well, I can't remember. God, there's so many, I can't remember. Mathematics, the sciences, and a couple of languages, English, and so on and so forth, history, geography, all that sort of thing. And so this went on till I was about 16. And then at age 16, one could drop the subjects you weren't good at or didn't like and specialize in just a few. And so I chose to specialize in the sciences. So from age 16 to 19 or 18 or 19, I did maths, physics, chemistry, and probably, I also think of biochemistry. So the rather specialized education. But of course, remember, up to age 16, I was doing, learnt about 3 languages, history, geography, and some, some science and maths. So there's it's quite a broad education to age 16, and it was in remarkable depth. And so the British education in general does a few subjects in great depth, or relatively great depth. And so you have to choose your subjects correctly, according to your talents. So it's very different from the American education, which is much broader and not so much depth. Which one is better? I don't think it's any difference. I mean, I don't think one's better than the other. You have to just look at the success Americans have in the science, in the sciences and in literature and so on and so forth, and also in the world of industry. I mean, Americans seem to have great success. So I think the British education is too narrow. But then, of course, it suits people like me much better, because people like me can only remember a maximum of 10 facts, and I'm not too sure of the last 4. And so I've had to survive by basically on a minimum of knowledge, because I can't remember very much, and so I had to survive by deducing things. And say this is rather different from the American education, where even at college, there's a lot of memory needed, because you're doing a huge number of different subjects. So there's no way you can survive on a bit of native cunning and so on, like I did. But you have to survive on memory and so on. So as far as I would say that my success is due to the fact that I had to survive on cunning and being able to deduce things. Because in research, that's what you do, right? Because you start with some problem that nobody's ever looked at before, and you have to figure it out. My whole life was built on this, at a much lower level. Even high school, basically, I had problems, and faced with an exam problem or something, And I didn't know anything. I couldn't remember anything, so I had to basically deduce everything from scratch. And so I had to live my wits all the time. And it's a bit of a strain, but I survived, and it worked well for me. I don't recommend everybody to do this because it's a bit dangerous, you see, because if I had not been able to deduce things from a few, from the few facts I could remember, I think I would have failed, right? And so it's up to you to which way you go.
Yes. We have time for maybe 2 or 3 questions. Yeah.
Hi, I guess I'll just piggyback a little bit off of that last question. So you talked a little bit about your education and how you had to kind of narrow down as time went on. So my question for you is, maybe not in your education, but in your other life, outside of that, or any time outside of that, did you do any art? And if so, did you do any art? Any of the arts? And if so, did they have a relationship with your physics?
As far as I was concerned, there was no relationship. As far as the art subject was concerned, to me, they seemed a little bit, sort of, I don't know, lacked logic. For instance, reading history, I couldn't understand why people did what they did. I mean, okay, it's in the record that they did this and then they did that, and this happened and that happened, but to me, why it all happened seemed totally illogical, so I could never really understand it. My memory wasn't good, so in order to succeed, even at the low level of this subject, I had to memorize it, remember who did what to whom, and why. And so it all was so illogical to me that it just became a mess in my head. I just couldn't do it. But things like maths and physics, as I said, I could manage on that by using my very little memory. I seem to have the ability to deduce things from just a few facts which my memory could hold. It just depends how your mind's made up.
Thank you.
Okay, you're welcome.
Hi. Excuse me if this is incorrect, but I'd heard that you're actually a very notable mountain climber back in the day. Is that true? And if so, how'd that happen?
I was a pretty fanatical rock climber, mountain climber, yeah. And I spent a lot of time in the mountains and climbing up cliffs and so on. I mean, I remember several times sitting on some ledge on a cliff somewhere, and while the leader was sort of struggling with some difficult thing, and then pictures of vortices and stuff were floating around my mind, and I would just sit there trying to follow these pictures, and have this stream of swear words from above because I was holding the rope and he couldn't move, and my leader couldn't move. So I had some experiences.
That was a part of your work.
Right.
Are you going to party at the award ceremony?
Not well. Okay, I will party to some extent, but I have to be careful how much alcohol I take because my health isn't as good as it should be, and so my balance is not what it was, and so after a bit of alcohol it becomes really bad, and so I have to be careful.
Hello, Professor. Among the various ways you could characterize your success, whether in the recognition, obviously, of your work, or the applications to electronics, or, as you've mentioned, the inherent satisfaction in solving a problem, what has been most rewarding for you?
To me, the most rewarding thing is the fun I had doing it, because more most of the problems I worked on, I found fascinating and fun. And so that is where my satisfaction is. Of course, getting recognition and getting this prize is wonderful and so on and so on, but it's not the main thing.
Thank you.
So let's give Professor Kosterlitz some time to prepare for tomorrow's trip. Let's thank Professor Kosterlitz for this opportunity.